The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Great. So what I'll talk about here is how to actually understand the performance of your application and what are some of the things you can do to actually improve your performance. You're going to hear more about sort of automated optimizations, compiler optimizations on Monday. There'll be 2 talks on that. And you'll get some cell-specific optimizations that you can do, some cell-specific tricks on Tuesday in the recitation. So here, this is meant to be sort of a more general purpose talk on how can you debug performance anomalies and performance problems, and then what are some ways that you can actually improve the performance? Where do you look after you've done your parallelization? So just to review sort of the key concepts to parallelism. Coverage. How much parallelism do you have in your application? And all of you know, because you all did, you had perfect scores on the last quiz. So that means you take a look at your program, you find the parallel parts, and that tells you how much parallelism that you have. If you don't have more than a certain fraction, there's really nothing else you can do with parallelism. So the rest of the talk will help you address the question of, well, where do you go for the last frontier? The granularity. We talked about how the granularity of your work, how much work are you doing in each processor, affects your load balancing, and how it actually affects your communication costs. If you have a lot of things co-located on a single processor, then you don't have to do a whole lot of communication across processors. But if you distribute things at a finer level, then you're doing a whole lot of communication. So we'll look at the communication costs again and some tricks that you can apply to optimize that. And then last thing we had talked about in one of the previous lectures is locality, and locality of communication versus computation. And both of those are critical. And so we'll have some examples of that. So just to review the communication cost model. So I had flashed up on the screen a while ago this equation that captures sort of all the factors that go into figuring out how expensive is it to actually send data from one processor to the other. Or this could even apply on a single machine where a processor is talking to the memory, loads and stores. The same cost model really applies there. And if you look at how processors, uniprocessor tries to improve communication, and some of the things we've mentioned really early on in the course for improving communication cost, what we focused on is this overlap. There are things you can do, for example, sending fewer messages, optimizing how you're packing data into your messages, reducing the cost of the network in terms of the latency, using architecture support, increasing the bandwidth, and so on. But really, the biggest impact that you can get is really just from overlap, because you have direct control over that, especially in parallel programming. But let's look at sort of a small review of what did it mean to overlap. So we had some synchronization point or some point in the execution, and then we sort of get data, and then once the data has arrived, we compute on that data. So this could be a uniprocessor, right? A CPU issues a load, it goes out to memory, memory sends back the data, and then the CPU can continue operating. But uniprocessors can pipeline this. They allow you to have multiple loads going out to memory, right? And so you can get the effect of hiding or overlapping a lot of that communication latency. But there are limits to the communication, to the pipelining effects, right? If the work that you're doing is really equal to the amount of data that you're fetching, then you have really good overlap. So we went over this in the recitation, and sort of we showed you an example of where pipelining doesn't have any performance effects, and so you might not want to do it because it doesn't give you the performance bang for the complexity you invest in it. So if things are really nicely matched, you get good overlap. Here you don't get good overlap. Sorry, these for some reason should be shifted over one. So where else do you look for performance? So there are 2 kinds of communication. There's the inherent communication in your algorithm, and this is sort of a result of how you actually partition your data and how you partition your computation. And then there's sort of artifacts that come up because of the way you actually do the implementation and how you map it to the architecture. So if you have poor distribution of data across memories, then you might unnecessarily end up fetching data that you might end up fetching data that you don't need, right? So you might also have redundant data fetches. So let's talk about that in more detail. And the way I'm going to do this is to sort of draw from wisdom in uniprocessors. So in uniprocessors, CPUs communicate with memory. And really conceptually, I think that's no different than multiple processors talking to multiple processors. It's really all about sort of where the data is flowing and how the memories are structured. So loads and stores are the uniprocessor as what and what are to distributed memories. So if you think of cell, what would go in those two blanks? Any guesses? I heard the answer there. Right, get and put. So DMA get and DMA put. That's really just a load and a store. It's just doing, instead of loading one particular data element, you're loading a whole chunk of memory. So on a uniprocessor, how do you overlap communication? Well, architectures, the memory system is designed in a way to exploit two properties that have been observed in computation: spatial locality and temporal locality. I'm going to look at each one separately. So in spatial locality, CPU asks for a data address 1000. What the memory does, it'll send data address 1000 plus a whole bunch of other data that's neighboring to it. So 1000 to 1064. And really, how much data you actually send, what is the granularity of the block? What is the granularity of the? Sorry. What is the granularity of the communication depends on sort of architecture parameters. So in common architectures, it's really the block size. So if you have a cache where the organization says you have a block size of 32 words, 32 bytes, then this is how much you transfer from main memory to the caches. So this works well when the CPU actually uses that data, right? If I send you 64 data bytes and I only use one of them, then what have I done? I've wasted bandwidth. Plus, I need to store all that extra data in the cache, so I've wasted my cache capacity. So that's bad, and you want to avoid it. Temporal locality is sort of a clustering of references in time. So if you access some particular data element, then what the memory assumes is you're going to reuse that data over and over and over again. So it stores it in the cache. So your memory hierarchy has the main memory at the top level, and that's sort of your slowest memory, but the biggest capacity. And then as you get closer and closer to the processor, you end up with smaller caches. These are local, smaller storage, but they're faster. And so if you reuse a data element, then it gets cached at the lowest data level. And so the assumption there is that you're going to reuse it over and over and over again. And if you do that, then what you've done is you've amortized the cost of bringing in that data over many, many references. And so that works out really well. But if you don't reuse that particular data element over and over again, then you've wasted sort of cache capacity. You still need to fetch the data because the CPU asked for it, but you might not have had to cache it, and so that would have created more space in your cache to have something else in there that might have been more useful. So in the multiprocessor case, how do you reduce these artifactual costs in communication? So you have these DMA receives, these DMA gets and puts on the cell, or just in just message passing, you're exchanging messages, and typically you're sort of communicating over a coarse or large blocks of data. And what you're usually getting is a continuous chunk of memory. Although you could do some things in software or in hardware to sort of scatter to gather data from different memory locations and pack them into contiguous locations. And the reason you pack them into contiguous locations, again, to sort of exploit spatial locality when you store the data locally. So to exploit the spatial locality characteristics, what you want to make sure is that you're actually going to have good spatial locality in your actual computation. So you want things that are iterating over loops with well-defined indices, that go over very short ranges, or they're very sequential or have fixed stride patterns where you're not wasting a lot of the data that you've brought in. Otherwise, you have to essentially just increase your communication because every fetch is getting you only a small fraction of what you actually need. So intuitively, this should make sense. Temporal locality just says, I brought in some data, and so I want to maximize its utility. So if I have any computation and in a parallel system, I might be able to reorder my tasks in a way that I have explicit control over the scheduling, which thread executes when, then you want to make sure that all the computation that needs that particular data happens sort of adjacent in time or in some short time window so that you can amortize the cost. Are those two concepts clear? Any questions on this? Okay. So you've done all of that. You've parallelized your code. You've taken care of your communication costs. You've tried to reduce it as much as possible. Where else can you look for performance? Things just don't look like they're performing as well as they could. And so the last frontier is perhaps single-thread performance. So I'm going to talk about that. So what is really a single thread? So if you think of what you're doing with parallel programming, you're taking a bunch of tasks. This is the work that you have to do. And you group them together into threads, or the equivalent of threads. And some threads will run on individual cores. So essentially, you have one thread running on a core. And if that performance goes fast, then your overall execution can also benefit from that. So that's single-thread performance. So if you look at sort of a timeline, here you have sequential code going on. Then we hit some parallel part of the computation. And we have multiple executions going on. Each one of these is a thread of execution. And really, my finish line depends on who's the longest sort of thread, who's the slowest one to complete. And that's going to essentially control my speed up. So I can improve this by doing better load balancing, right? If everybody is, if I distribute the work such that everybody's doing equivalent amount of work, then I can shift that finish line earlier in time. And that can work reasonably well. And so we talked about load balancing before. But you can also make execution on each processor faster. If each one of these threads finishes faster, or I've done the load balancing and now I can even squeeze out more performance by shrinking each one of those lines, then I can get performance improvements there as well. So that's improving single thread performance. But how do we actually understand what's going on? How do I know where to optimize? How do I know how long each thread is taking? How do I know how long my program is taking? Where are the problems? And so there are performance monitoring tools that are designed to sort of help you do that. So what's the sort of most coarse-grained way of figuring out how long your program took? You have some sample piece of code shown over here. You might compile it, and then you might just use time. Standard Unix command, sort of say, run this program and tell me how much time it took to run. So you get some output back from time that says you took about 2 seconds of user time. This is the actual code. You took some small amount of time in system code. And this is your overall execution. This is how much of the processor you actually use. So a 95% utilization. Then you might apply some optimizations. So here we'll use the compiler. We'll change the optimization level, compile the same code, run it. And we'll see, wow, performance improved. And so we increased 99% utilization. My running time went down by a small chunk. But did we really learn anything about what's going on here? There's some code going on. There's a loop here. There's a loop here. There's some functions with some more loops. So where's the actual computation time going? So how would I actually go about understanding this? So what are some tricks you might have used in trying to figure out how long something took in your computation? Say that louder.
For example, start and stop the timer outside of different loops.
Right. So you might have a timer. You record the time here. You compute, and then you stop the timer, and then you might print out or record how long that particular block of code took. And you might have a histogram of them, and then you might analyze the histogram to find out the distribution. And you might repeat this over and over again for many different loops or many different parts of the code. And if you have an idea of, you have a preconceived notion of where the problem is, then you instrument that and see if your hypothesis is correct. And that can help you sort of identify the problems. But increasingly, you can actually get more accurate measurements. So in the previous routine, you were using the time. We were looking at the sort of how much time has elapsed in seconds or in small increments. But you can actually use hardware counters today to actually measure clock cycles, clock ticks. And that might be more useful. And actually, it's more useful because you can measure a lot more events than just clock ticks. And the counters in modern architectures are really specialized registers that count up events. And then you can go in there and sort of probe it and ask, what is the value in this register? And you can use that as part of your performance tuning. And you use them much in the same way as you would have done to sort of start a regular timer or stop a regular timer. There are specialized libraries that run. Unfortunately, these are very architecture specific at this point. There's not really a common standard that says grab a timer at each different architecture in a uniform way, although that's getting better with some standards coming out from, and I'll talk about that in just a few slides. And you can use this to, for example, measure your communication to computation cost. So you can wrap your DMA get and DMA put by timer calls, and you can measure your actual work by timer calls and figure out how much overlap can you get from overlapping communication and communication and computation, and is it really worthwhile to do pipelining? But this really requires manual changes to your code, right? You have to go in there and insert the timers. You have to have maybe an idea of where the problem is. And you have the Heisenberg effect. You know, if you have a loop and you want to measure code within the loop because you have a nested loop inside of that, then now you're affecting the performance of the outer loop. That can be problematic, right? So the Heisenberg effect says you can't really make an accurate measurement on the thing you're inspecting. So there's a slightly better approach, dynamic profiling. And dynamic profiling is really there's an event-based profiling and time-based profiling. Conceptually, they do the same thing. What's going on here is your program is running, and you're going to say, I'm interested in events such as cache misses. Whenever n number of cache misses happen, let's say 1,000, let me know. So you get an interrupt whenever 1,000 cache misses happen. And then you can update a counter or use that to sort of trigger some optimizations or analysis. So this works really nicely because you don't have to touch your code. You essentially run your program as you normally do with just one modification and includes sort of running the dynamic profiler as well as your actual computation. It supports multiple languages because all it does is just takes your binary, so you can program in any language, any programming model. And it's quite efficient to actually use these dynamic profiling tools. And the sampling frequencies are reasonably small. You can make them reasonably small and still have it be efficient. So some counter examples. Clock cycles, so you can measure clock ticks. Pipeline stalls. This might be interesting if you're doing sort of, you want to optimize your instruction schedule. You'll actually see this in the recitation next week. Cache hits, cache misses, you can get an idea of how bad your cache performance is and how much time you're spending in the memory system, number of instructions, loads, stores, floating point ops, and so on. And then you can derive some useful measures from that, right? So I can get an idea of processor utilization, right? Divide cycles by time, and that gives me utilization. I can derive some other things, maybe some of the more interesting things like memory traffic. So how much data am I actually sending between the CPU and the processor? Or how much data am I communicating from one processor to the other? So I can just grab the counters for a number of loads and number of stores, figure out what the cache line size is. Usually those are documented, or there are calibration tools you can run to get that value, and you figure out memory traffic. Another one would be bandwidth consumed. So bandwidth is memory traffic per second. So how would you measure that? Right. It's just the traffic divided by the wall clock time. There's some others that you can calculate. So these can be really useful in helping you figure out where are the things you should go focus in on. I'm going to show you some examples. The way these tools work is you have your application source code, you compile it down to a binary. You take your binary and you run it, and then that can generate some profile that's stored sort of locally on your disk. And then you can take that profile and analyze it by some sort of interpreter. And in some cases, you can actually analyze the binary as well and re-annotate your source code. And that can actually be very useful because it'll tell you this particular line of your code is the one where you're spending most of your time computing. So some tools, have any of you used these tools? Anybody use gprof, for example? Okay, good. So you might have an idea of how these could be used. There are others. HPC Toolkit, which I commonly use from Rice. PAPI is very common because it has a very nice interface for grabbing all kinds of counters. vTune from Intel, and there's others that work in different ways. So there are binary instrumenters that do the same things and do it slightly more efficiently, and actually give you the ability to compile your code at runtime and optimize it, taking advantage of the profiling information you've collected. So here's a sample of running gprof. gprof should be available on any Linux system. It's even available on Cygwin if you use Cygwin. I've compiled some code. This is MPEG-2 decoder reference implementation. I specify some parameters to run it. And here I add this -r flag, which says use a particular kind of inverse DCT that's floating point precise. It uses double precision for the floating point computations in DCT. Inverse DCT, rather. And so you can see that's actually where most of the time is being spent in the computation. So here's the time per function. So each row represents a function. cumulative time. So this is this is the percent of the time. This is the actual time in seconds. How many times I actually call this function, and some other useful things. So the second function that's used here that happens is MPEG intra-block decoding, and here you're doing some spatial decomposition, restoring spatial pictures, about 5%. So if you were to optimize this particular code, where would you go look? Right, you would look in the reference DCT. So MPEG has two versions of DCT, one that uses floating points, another that just uses some numerical tricks to operate over integers for a loss of precision, but they find that acceptable as part of this application. So if you omit the R flag, it actually uses a different function for doing the DCT, and now you see the distribution of where the time is spent in your computation changes. So now there's a new function that's become the bottleneck, and it's called form component prediction. And then IDCT column, which actually is the main replacement of the previous code, this one is now about a third of the actual computation. So this could be useful because you can gprof your application, figure out where the bottlenecks are in terms of performance, and you might go in there and tweak the algorithm completely. You might go in there and sort of look at some problems that might be sort of implementation bugs or performance bugs and be able to fix those. Any questions on that? Okay. You can do sort of more accurate things. So gprof largely uses one mechanism. HPC toolkit uses the performance counters to actually give you more finer grade measurements if you want them. So in the HPC toolkit, you run your program in the same way. You have MPEG-2 decode. -- just says this is where the parameters are to MPEG-2 decode, following that -- And you can add some parameters in there that say, these are the counters I'm interested in measuring. So the first one is total cycles. The second one is the L1, so primary cache load misses. And then you might want to count the floating point instructions and the total instructions. So as you run your program, you actually get a profiling output, and then you can process that file, and it'll spit out some summaries for you. So it'll tell you, this is the total number of cycles, 698 samples with this frequency. So if you multiply the two together, you get an idea of how many cycles your computation took. How many load data misses? It says 27 samples at this frequency. So remember what's going on here is the counter is measuring events, and when the event reaches a particular threshold, it lets you know. So here the sampling threshold is 32,000, and so whenever 32,000 floating point instructions occur, you get a sample. So you're just counting how many interrupts you're getting or how many samples. So you multiply the two together, you can get the final counts. And it can do things like gprof. It'll tell you, where your time is and where you spent most of your time. Actually breaks it down into your module. So MPEG calls some standard libraries, libc. It can break it down by function, break it down by line number, and you can even annotate your source code. So here's just a simple example that I used earlier, and you can actually, each one of these columns represent one of the metrics that we measured, and you can see, most of my time is spent here, 36% at this particular statement. So that can be very useful. You can go in there and say, I want to do syndization. I can maybe reduce this overhead in some way to get better performance. Any questions on that? Yep.
Does HPC Prep support kernel profiling?
I don't know. Yeah, unfortunately, I don't know the answer to that. There's some nice GUIs for some of these tools. So vTune has a nice interface. I use HPC Viewer, so I just I use HPC Toolkit, which provides HPC Viewer. So I just grabbed a screenshot from one of the tutorials on this. And you have your source code. It shows you some of the same information I had on a previous slide, better in a nicer graphical format. Okay, so now I have all this information. How do I actually improve the performance? Well, if you look at what is the performance time on a uniprocessor, it's time spent computing plus the time spent waiting for data or waiting for some other things to complete. And you have instruction level parallelism, which is really critical for uniprocessors, and architects have sort of spent massive amounts of efforts in providing multiple functional units, deeply pipelining the instruction pipeline, doing things like speculation and prediction to keep that instruction level parallelism number high so you can get really good performance. And you can do things like looking at the assembly code and reordering instructions to avoid instruction hazards in the pipeline. You might sort of look at a register allocation, but that's really very low-hanging fruit. You have to reach really high to grab that kind of fruit. And you'll actually, unfortunately, get to experience that as part of the next recitation. So apologies in advance. But you'll see that I'm not going to talk about that. Instead, I'm going to focus about some things that are perhaps lower-hanging fruit. So data level parallelism. So we've used SIMD in some of the recitations, sort of giving you a short example of that. Here, I'm going to talk about how you actually get data level parallelism, or how do you actually find the SIMD in your computation so you can get that added advantage. Some nice things about data level parallelism in the form of short vector instructions is that the hardware really becomes simpler. You issue one instruction, and that same instruction operates over multiple data elements, and you get better instruction bandwidth. I just have to fetch one instruction, and if my vector length is 10, then that effectively does 10 instructions for me. The architecture can get simpler, it reduces the complexity. So it has some nice advantages. The other thing to go after is the memory hierarchy. And this is because of sort of that speed gap that we showed earlier on in the course between memory speeds and processor speeds. And if you optimize the performance, usually like 1% performance in your cache miss rate gives you some significant performance improvement in your overall execution. So you want to sort of go after that because that's sort of the biggest beast in the room. So a brief overview of SIMD, and then sort of some detailed examples as to how you actually go about extracting short vector instructions. So here we have an example of scalar code. We're iterating in a loop from 0 to n, and we're just doing adding some array elements A to B and storing the results in C. So in a scalar mode, we just have one add. Each value of A and B is one register. We add those together, we write the value to a separate register. In the vector mode, we can pack multiple data elements. So here, let's assume our vector length is 4. I can pack 4 of these data values into one vector register. I can pack 4 of these data elements into another vector register. And now my single vector instruction has the effect of doing 4 adds at the same time. And it can store results into 4 elements of C. Any questions on that?
Is that the actual syntax you use for the cell processing?
No, we'll get to that. So what would, let's look at the sort of give you a more lower level feel for this. Same code, I've just shown a data dependence graph. I've omitted things like the loads and the increment of the loop and the branch, just focusing on the main computation. So I have 2 loads, one brings A sub I, the other brings B sub I. I do the add, and I get C sub I, and then I can store that. So that might be sort of a generic opcode sequence that you have. And if you're scheduling that, then in the first slot I can do those 2 loads in parallel. Second cycle I can do the add. Third cycle I can do the store. I can further improve this performance. So if you took 6035, you might see software pipelining. You can actually overlap some of these operations. Not really that important here. So what would the sort of the schedule look like on a cycle-by-cycle basis if this was the vector opcodes? Well, in the scalar case, you have n iterations, right? Each iteration is taking 3 cycles, so that's your overall execution runtime, n times 3 cycles. In the vector case, each load is bringing you 4 data elements, so A sub I to A sub I plus 3. Similarly for B, and then you add those together. So the schedule would look essentially the same. The opcodes are different. And here, what should your overall execution time be? Well, what I've done is each iteration is now doing 4 additions for me. So if you notice, the loop bounds have changed. Instead of going from I to n by increments of 1, now I'm going by increments of 4. So overall, instead of having n iterations, I can get by with n over 4 iterations. Does that make sense? So what would my speed up be in this case? 4, right? So you can get more and more speed up if your vector length is longer, right, because then I can cut down on the number of iterations that I need. And depending on the length of my vector register and the data types that I have, that effectively gives me different kinds of vector length for different data types. So you saw on cell you have 128-bit registers, and you can pack those with bytes, characters, shorts, integers, floats, or doubles. And so each one of those gives you different kinds of a different vector length. And SIMD is really now, SIMD extensions are increasingly popular. They're available in a lot of ISAs. So the AltiVex, MMX, SSE are available in a lot of x86 machines. And of course in Cell, in fact on the SPU, all your instructions are SIMD instructions. And when you're doing a scalar instruction, you're actually using just one chunk of your vector register and your vector pipeline. So how do you actually use these SIMD instructions? Unfortunately, it's library calls, or using inline assembly, or using intrinsics. And you'll get hands-on experience with this with Cell, so you might complain about that when you actually do it. Compiler technology is actually getting better, and you'll see that one of the reasons we're using the XLC compiler is because it has these vector data types, which also latest versions of GCC have, that allow you to sort of express data types as vector data types, and the compiler can more easily or more naturally sort of get the parallelism for you, SIMD parallelism, without you having to go in there and sort of do it by hand. But if you are to do it by hand, or in fact what the compilers are trying to automate, are different techniques for sort of looking for where the SIMD parallelism is. There's some work done here about 6 years ago by Sam Larson, who's now graduated, on superword level parallelism. So I'm going to focus the rest of this talk on sort of this concept of SIMDization, because I think it's probably the one that's most useful for extracting parallelism in some of the codes that you're doing. So this is really ideal for SIMD, where you have really short vector length, 2 to 8. And what you're looking for is SIMDization that exists within a basic block. So within a code block, within a body of a loop, or within some control flow even. And you can uncover this with simple analysis, and this is really sort of has pushed the boundary on what automatic compilers can do. And some of the work that's gone on at IBM, what they call the octopiler, has eventually been transferred to the XLC compiler, sort of do a lot of these techniques that build on SLP and sort of expand in various ways to broaden the scope of what you can automatically parallelize. So here's sort of an example of how you might actually derive SIMDization. Or opportunities for SIMDization. So you have some code, let's say you're doing RGB computations where you're just adding the R element, so red, green, and blue. And so this might be in a loop, and what you might notice is, well, I can pack the RGB elements into one register, I can pack these into another register, and I can pack these literals into a third register. And so that gives me a way to sort of pack data together into SIMD registers. And now I can replace this scalar code with a way to instructions that pack the vector register. I can do the computations in parallel, and I can unpack them. And we'll talk about that with a little bit more illustration in a second. Any questions on this? Okay. Perhaps the biggest improvement that you can get from SIMDization is by looking at adjacent memory references. And rather than doing one load, you can do a vector load, which really gives you a bigger bandwidth to memory. So in this case, I have a load from I0, I1, I2. And since these memory locations are contiguous, I can replace them by one vector load that brings in all these data elements in one shot. And that essentially eliminates 3 load instructions, which are potentially the heaviest, most heavyweight, for one lighter weight instruction, because it amortizes bandwidth and it exploits things like spatial locality. Another one, vectorizable loops. So this is probably one of the most advanced ways of exploiting SIMDization, especially in really long vector codes, so traditional supercomputers like the Cray. And you'll probably hear Saman talk about this in the next lecture. So I have some loop, and I have this particular statement here. So how can I get SIMD code out of this? Anybody have any ideas? Anybody know about loop unrolling? Okay, so if I unroll this loop, I essentially, that same trick that I had shown earlier, although I didn't quite do it this way, I change the loop bounds from n to, for the increment from, rather than stepping through one at a time, stepping through four at a time. And now the loop body, rather than doing one addition at a time, I'm doing 4 additions at a time. So now this is very natural for vectorization, right? Vector load, vector store, plus the vector add in the middle. Is that intuitive? Okay. So this gives you another way of sort of extracting parallelism, looking at traditional loops, seeing whether you can actually unroll it in different ways, sort of be able to get that SIMD parallelization. And the last one I'll talk about is about partial vectorization. These might be some things where you have a mix of statements. So here I have a loop where I have some load, and then I'm doing some computation here. So what could I do here? It's not as symmetric as the other loop.
There's no vector times the value function, at least it's just a serialized value function.
Right, so you might omit that, but could you do anything about the subtraction? Okay, so I can unroll this again, right? And now there's no dependencies between this instruction and this instruction, right? So I can really move these together. And once I've moved these together, then these loads become contiguous. These loads are contiguous. So I can replace these by vector codes, vector equivalents, right? So now the vector load brings in L0, L1. I have the addition that brings in those 2 elements in a vector. And then I can do my vector, my scalar additions. But what do I do about the value getting out of this vector register into the scalar register that I need for the absolute values? So this is where sort of the benefits versus costs of summarization come in. So the benefits are great because you can have, you can replace multiple instructions by one instruction, or you can just cut down the number of instructions by a specific factor, your vector length. Load stores can be replaced by one wide memory operation, and this is probably the biggest opportunity for performance improvements. But the cost is that you have to pack data into the vector registers, and you have to unpack it out so that you can have those kinds of communications between this vector register here and the value here, this value here, and this value here. Often you can't simply access vector values without doing this packing and unpacking. Okay, so how do you actually do the packing, unpacking? And this is predominantly where a lot of the complexity goes. So you might notice, whoops, screwed up animation. So the value of A here is initialized by some function, and the value of B here is initialized by some function, and these might not be things that I can SIMDize very easily. So what I need to do is move that value into the first element of vector register, and then move the second value into the second element of the vector register. So if I have a 4-way vector register, then I have to do 4 of these moves, and that essentially is the packing. Then I can do my vector computation, which is really these 2 statements here. And then eventually I have to do my unpacking because I have to get the values out to do this operation and this operation. So there's an extraction that has to happen out of my SIMD register. But you can amortize the cost of the packing and unpacking by just reusing your vector registers. So these are like register allocation techniques. So if I've packed things into a vector register, I find all cases where I can actually reuse that vector register, and I try to find opportunities for extra SIMDization. So in the other case, then I pack one, then I can reuse that same vector register. So what are some ways I can look for to amortize the cost? And the interesting thing about memory operations is while there are many different ways you can pack scalar values into a vector register, there's really only one way you can pack loads coming in from memory into a vector register. That's because you want the loads to be sequential, you want to exploit the spatial locality, so one vector load really gives you specific ordering. And so that really constrains you in various ways. And so you might bend over backwards in some cases to actually get your code to be able to reuse sort of the wide word load without having to do too much packing or unpacking, because that'll start sort of eating into your benefits. So a simple example of how you might find the SLP parallelism So the first thing you want to do is start with sort of the instructions that give you the most benefit. So it's memory references. So here there are two memory references. They happen to be adjacent, so I'm accessing contiguous memory chunks. So I can parallelize that. So that would be my first step. I can do a vector load, and that assignment can become A and B. And then I can look for opportunities where I can propagate this vector values in this vector register that's holding A and B. Well, so the way I do that is I look for uses of A and B. So in this case, there are these two statements. Okay, so I can look for opportunities to vectorize that. And so in this case, both of these instructions are also vectorizable. So now I have vector subtraction, and I have a vector register holding new values, H and J. So I follow that chain again of where the data is flowing. So I find these operations, and I can vectorize that as well. Okay, so I end up with a vectorizable loop where all my instructions, all my scalar instructions, are now in SIMD instructions. And I can cut down on sort of loop iterations, total number of instructions that I issue, but I've made some implicit assumption here. Anybody know what it is? Yep, Micah.
Do you actually need that many iterations of the loop?
Well, so you can factor down the cost, right? So here I've vectorized by 2, so I would cut down the number of iterations by 2.
Right, but you could have an odd number of iterations.
Right, so you could have an odd number of iterations. What do you do about sort of the remaining iterations? You might have to do scalar code for that. What are some other assumptions? Maybe it'll be clear here. So in vectorizing this, what have I assumed about sort of relationships between these statements? I've essentially reorganized all the statements, so it assumes I have this liberty to move instructions around. Yep.
Assuming that A and B don't change after you do it.
Right. So there's nothing in here that's changing the values. And there's no dependencies between these statements, no flow dependencies, and no other kinds of constraints that sort of limit this kind of movement. So in real code, it's not actually the case. You end up with patterns of computation where you can get really nice cases, classic cases. You can vectorize those really nicely. But in a lot of other codes, you have a mix of vectorizable code and scalar code, and there's a lot of communication between the two. So the cost is really quite something significant that you have to consider. So this was, as I mentioned, done in somebody's master's thesis, and eventually led to some additional work that was his PhD thesis. And so in some of the early work, what he did was he looked at a bunch of benchmarks and looked at how much available parallelism you have in terms of this kind of short vector parallelization, or rather SLP, where you're looking for vectorizable code within basic blocks, which really differed from classic way of people looking for vectorization and really well-structured loops and doing kinds of transformations you'll hear about next week. And so for different kinds of vector registers, so these are your vector length, so going from 128 bits to 1024 bits, you can actually reduce a whole lot of instructions. So what I'm showing here is the percent dynamic instruction reduction. So if I take my baseline application and just compile it in a normal way and I run it, I get an instruction count. I apply this SLP technique to sort of find the SIMDization and then run my application again. Use the performance counters to count the number of instructions, and I sort of compare the two. I can get 60%, 50%, 40%. In some cases, I can completely eliminate almost 90% or more of the instructions. So it's a lot of opportunity for sort of performance improvements that might be apparent. One, because I'm reducing the instruction bandwidth. I'm reducing the amount of space I need in my instruction cache. I have fewer instructions, so I can fit more instructions into my instruction cache. You reduce number of branches. You get better bandwidth to memory, better use of the memory bandwidth. And overall, you're running fewer iterations, so you're getting lots of potential for performance. So actually ran this on the AltaVec. This was sort of one of the earliest generations of AltaVec, which had SIMD instructions. Didn't have, I believe, double floating. Double precision floating point. So not all the benchmarks you see on the previous slide are here. only the ones that could run reasonably accurately with a single precision floating point. And so what they measure is the actual speed up. Doing the simulation versus not doing the simulation, how much performance you can get. And the thing to take away is, in some cases where you have nicely structured loops and some nice patterns, you can get up to a 7x speed up on some benchmarks. And so what might be the maximum speed up that you can get, it depends on the vector length. So 8, for example, on some architectures, depending on the data type. So any questions on that? So as part of the next recitation, you'll actually get an exercise of going through and simdizing for cell. And what does it actually mean to simdize instructions for cell? Well, it might take statements and sort of replace them by intrinsic functions, which eventually map down to actual assembly opcodes that you'll need. So you don't actually have to program at the assembly level, although in effect, you're probably doing the same thing. OK, so last thing we'll talk about today is sort of optimizing for the memory hierarchy. And in addition to sort of data level parallelism, looking for performance enhancements in the memory system gives you the best opportunities because of sort of this big gap in performance between memory access latencies and what the CPU efficiency is. So exploiting locality in the memory system is key. So these concepts of temporal and spatial locality. So let's look at an example. So let's say I have a loop, and in this loop I have some code that's embodied in some function A, some code embodied in some function B, and some code in some function C. The values produced by A are consumed by the function B, and similarly the values consumed by B are consumed by C. So this is sort of a general data flow graph that you might have for this function. Let's say that we can produce all the data could go into a small array that then I can sort of communicate between functions. So if I look at my actual cache size and how the working set of each of these functions is, so let's say this is my cache size. This is how many instructions I can pack into the cache. And looking at the collective number of instructions in each one of these functions, I sort of overflow that. I have more instructions that I can fit into my cache at any one time. So what does that mean for my actual cache performance? So when I run A, what do I expect the the cache hit and miss rate behavior to be like? So in the first iteration, I'm going to run, I need the instructions for A. Right? I've never seen A before, so I have to fetch that data from memory and put it in the cache. So it'll be a cache miss, right? OK. So what about B? Right, and then C? Same thing. OK, so now I'm back at the top of my loop. Right? So if everything fit in the cache, then I would expect A to be a what? Right? It would be a hit. But since I've sort of constrained this problem such that the working set doesn't really fit in the cache, what that means is that I have to fetch some new instructions for A. So let's say I have to fetch all the instructions for A again. So that leads me to another miss, right? And now bringing A again into my cache kicks out some extra instructions because I need to make room in a finite memory. So I kick out B. And bring in B, and I end up kicking out C. And so you end up with a pattern where everything is a miss. So this is a problem because the way the loop is structured, collectively I just can't pack all those instructions into the cache. So I end up taking a lot of cache misses, and that's bad for performance. But I can look at an alternative way of doing this loop. I can split up this loop into 3, where in one loop I do all the A instructions. In the second loop I do all the B's. And in the third loop I do all the C's. So now my working set is really small, right? So the instructions for A fit in the cache, instructions for B fit in the cache, and instructions for C fit in the cache. So what do I expect for the first time I see A and miss? And then the second time? What? It'll be a hit, right? Because I brought in A. I haven't run B or C yet. The number of instructions I need for A is smaller than what I can fit into the cache, so that's great. Nothing gets kicked out. So every one of those iterations for A becomes a hit. So that's good. I've improved performance. For B, I have the same pattern. Right? First time I see B, it's a miss. Every time after that, it's a hit. And similarly for C. So my cache miss rate goes from So being 1, everything is a miss, to decreasing to 1 over n, where n is essentially how much I can run the loop. So we call that full scaling because we've taken sort of the loop and we've distributed, and we've scaled every one of those smaller loops to the maximum that we can get. Now, what about the data? So we have the same example. Here we saw that the instruction working set is big, but what about the data? So let's say, in this case, I'm sending just a small amount of data, then the behavior is really good, right? My data working set, it's a small amount of data that I need to communicate from A to B. It's a small amount of data I need to communicate from B to C. So that's great. No problems with the data cache. What happens in the full scaling case?
It's not even correct, right? A needs to communicate.
Say again?
It's not even correct, right? A needs to communicate with B.
What do you mean it's not correct?
Well, it doesn't say it has
it
to
just-
communicate at the same time.
Oh, it's not communicating in the same
Yeah, it's not at
direction.
the same time. It's just saying, but in fact, just assume this is sequential, right? So I run A, I store some data, and then when I run B, I grab that data.
Well, but then,
Just assume sequential, nothing.
but then how do you know that how do you know that the transformation is valid then? B could use some global variable written by A, right?
Simple case. There's no global variables. All the data that B needs comes from A. So if I run A, I produce all the data, and that's all that B needs. Okay, so in the full scaling case, what do I expect to happen for the data? Remember, in the full scaling case, all the working sets for the instructions are small, so they all fit in the cache. But now I'm running A for a lot longer, so I have to store a lot more data for B. And similarly, I'm running B for a lot longer, so I have to store a lot more data for C. So what do I expect to happen with the working set here? Right? Instructions are still good, but the data might be bad because I've run A for a lot more iterations at one shot. So now I have to buffer all this data for A to B. And similarly, I've run B for a long time, so I have to buffer a whole lot of data for B to C. Is that clear?
No.
No. So let's say every time A runs, it produces one data element.
Right.
So now, in this case, every iteration produces one data element. That's fine.
Okay.
That's clear? Here, I run A n times, so I produce n data elements, right? And B, let's say, produces one data element. So if my cache can only hold, let's say, n by 2 data elements, then there's an overflow. So what that means is not everything is in the cache, and that's bad because of the same reasons we saw for the instructions. When I need those data, I have to go out to memory and get them again. So it's extra communication, extra redundancy.
In this case, though, you don't need to store the A variables you're going B to C, and you just distribute it across. So you actually.
But no distributed, just sequential, simple case, right? I need all the data from A to run all the iterations for B.
Right.
And then, yeah, this goes away, right? So let's say this goes away.
Oh, okay.
But still B produces n elements, and that overflows the cache. Okay. So there's a third example where I don't fully distribute everything. I partially distribute some of the loops. So I can fully scale A and B because I can fit those instructions in the cache. And that gets me around this problem, right? Because now A and B are just communicating one data element. But C is still a problem because I still have to run B n times in the end before I can run C, so there are n data elements in flight. Right? So the data for B still becomes a problem in terms of its locality. Is that clear? Okay. So any ideas on how I can improve this? Mike?
Just a question.
Yeah.
Are data misses not as bad as instruction misses? Because assuming if you have a long cache line, I mean, you're only gonna have to do 1 or 2 extra, memory accesses to get the data that doesn't fit in cache.
So in programs, programs typically have really good instruction locality, just because of the nature of the way we run them. We have small loops, and they iterate over and over again. Data is actually where you spend most of your time in the memory system. It's fetching data. So I didn't actually understand why you think data is less expensive than instructions.
What I'm saying is, like, if you say you want to read an array, right? You read the first, say, like 8 elements to fit 8 words in the cache line.
Okay.
Well, then you get 7 hits, but then, so every 8 iterations you have to do a read as opposed
Right.
to.
Right. So that assumes that you have really good spatial locality, right? Because you've assumed that I've brought in 8 elements and I'm going to use every one of them. So if that's the case, you have really good spatial locality, and that's in fact what you want. Right? It's the same kind of thing that I showed for the instruction cache. The first thing is a miss, the rest are hits. The reason data is more expensive, you simply have a lot more data reads than you have instructions. Typically, you have small loops, hundreds of instructions, and they might access really big arrays that are millions of data references. So that becomes a problem. Okay. So ideas on how to improve this? Yep. Nested loop. So what would you do in the smaller loop? Something like that? Okay. So in the nested loop, right, you have a smaller loop that has a smaller number of iterations, so 64. And 64 might be just as much as I can buffer for the data in the cache. And then I wrap that loop with one outer loop that completes the whole number of iterations. So if I had to do n, then I divide n by 64. And so that can work out really well. So there are different kinds of blocking techniques that you can use on getting your data to fit into your local store or into your cache to exploit sort of these spatial and temporal properties. Question?
Would it not be better to use a small enough loop size so you could run ABC sequentially?
You could do that as well. But the problem with running ABC sequentially is that if they're all in the same loop, you end up with instructions being bad. And that was really this case. So even if you change this number, you don't get around the instructions. Okay. So you're going to see more optimizations that sort of do more of these loop tricks. I talk about unrolling without really defining what unrolling is or going into a lot of details. Loop distribution, loop fission, some of the things like loop tiling, loop blocking. I think Saman's going to cover some of these next week. So this was implemented. This was done by another master's student at MIT, graduated about 2 years ago, to sort of show that if you factor in cache constraints versus ignoring cache constraints, how much performance you can get. This was done in the context of Streamit. So in fact, some of you might have recognized sort of A to B to C being interconnected as a pipeline of filters. And we ran it on different processors. So a strong arm processor is really small. In-order processor has no L1 cache in this particular model that we used, but it had a really long latency to, it had no L2 cache. It had a really long latency to memory. A Pentium, an x86 processor, reasonably fast. It had a complicated memory system and allowed a lot of memory overlap in terms of references. And then the Itanium processor, which had a huge L2 cache at its disposal. So what you can see is that lower bars indicate bigger speedups. This is normalized runtime. So on the processor where you don't actually have caches to save you and the memory communication is really expensive, you can get a lot of benefit from doing the cache-aware scaling, sort of that loop nesting, to take advantage of packing instructions into the instruction cache, packing data into the data cache, and not having to go out to memory if you don't need to. So you can reduce runtime to about a third of what it was with this kind of cache optimization. On the Pentium 3, where you have sort of a cache to help you out, the benefits are there, but you don't get as big a benefit from sort of ignoring the cache constraints versus being aware of the cache constraints. So here you're actually doing some of that middle column, whereas here we're doing the third column, sort of the cache-aware fusion. And in Itanium, we really get no benefits between the two. Yeah.
Could you explain what the left columns are?
These?
Yeah.
So this is, tricky. Probably should have ignored that. So the left columns are doing this.
So just assuming that iCache is
Right, and the third column is doing this. Right, so you want to do this because the iCache locality is best. So you always want to go to full or maximum scaling. I'm actually fudging a little just for the sake of clarity. And here you're actually doing this nesting to improve both the instruction and the data locality. Okay, so you can get really good performance improvements. So what does that mean for your cell projects or for cell? We'll talk about that next week on the recitation. Yeah?
Is there something to read from the fact that there's no improvement on that?
Well, it just means that if you have caches to save you, and they're really big caches and they're really efficient, it's law of diminishing returns. So that's where profiling comes in. So you look at the profiling results, you look at your cache misses, how many cache misses are you taking? If it's really significant, then you look at ways to improve it. If your cache misses are really low, your miss rate is really low, then it doesn't make sense to spend time and energy focusing on that. Good question. Okay, so any other questions? All right, so summarizing sort of the gamut of programming for performance. So you tune the parallelism first, right? Because if you can't find a concurrency, Amdahl's law, you're not going to get a whole lot of speed up. But then once you've sort of figured out what the parallelism is, then what you want to do is really get the performance on each processor, the single thread performance, to be really good. You shouldn't ignore that. So modern processors are complex. You need instruction level parallelism, you need data level parallelism, you need memory hierarchy optimizations, and you should consider sort of those optimizations. And here profiling tools could really help you figure out where the biggest benefits to performance will come from. And you may have to, in fact, change everything. You may have to change your algorithm, your data structures, your program structure. So in the MPEG decoder case, for example, I showed you that if you change the flag that says don't use double precision inverse DCT, use a sort of a numerical hack, then you can get performance improvements, but you're changing your algorithm really. And you really want to focus on just the biggest nuggets. Where's the most of the performance coming in, or where's the biggest performance bottleneck, and that's the thing you want to optimize. So remember the law of diminishing returns. Don't spend your time on doing things that aren't going to get you anything significant in return. And that's it. Any questions? Okay. How are you guys doing with the projects? So one of the added benefits of the central CVS repository is I get notifications too when you submit things. So I know of only 2 projects that have been submitting things regularly. So I hope that'll pick up soon. Okay. I guess a few minutes to finish the quiz, and then we'll see you next week. Have a good weekend.